Hi, welcome to this machine learning presentation. I did a quantum computing qubit pattern classification project using recurrent neural networks with LSTM. So my agenda is I'm going to give an overview of the project and what my goal was. I'll talk about how I selected the data set. I'll talk about our project plan. Then I'll run through the exploratory data analysis, my results, and my conclusion. So, patent offices around the world issue millions of patents every year. And some companies have large patent portfolios, and it's hard for those companies to understand and manage their patent assets for a specific technology area. Now, machine learning can help automate tasks that have previously been exclusively handled by human beings. So, this project is an attempt to demonstrate the ability of machine learning to classify patents as belonging in a particular category of asset. In this particular case, the data set is about whether a patent relates to quantum computing qubit technology. I'm going to use patent metadata information, the title, the publication date, the serial number, the family ID. While we could possibly get more accurate results with the full text and drawings of a full patent document, that would require more processing power. So my goal is to analyze patterns with deep learning, and I was focusing in on long short-term memory for analyzing sequential text information related to patents. Patent documents include the body of the patent document, which is the specification text, the claims, the drawings, as well as patent metadata, text and numeric data. And again, analyzing the body of the patent documents is beyond the scope of this project, and I'm focusing on patent metadata for this binary classification problem, whether or not the patent is related to qubits or not. And I'm going to actually compare and contrast LSTM, bidirectional LSTM, and gated recurrent units. So the data set I found is called the quantum computing gold standard. I looked on Kaggle, couldn't find anything useful. Eventually, I found this quantum computing classification gold standard located on GitHub. Data set was created by Tony Tripp, and Steve Harris, Tony Tripp, David Chalice, and Nigel Switcher have an article about the data set. So here's our problem description. Qubit generation for quantum computing refers to patents that discuss the means of generating qubits for use in a quantum mechanics-based computing system. So patent documents that are positive, that is, they're related to qubits, would talk about things like superconducting loops, topological quantum dot-based, ion traps, and so on. Patent documents that are negative would not have those aspects. We would talk about other things. Perhaps they talk about applications, algorithms, and or don't mention hardware or mention hardware that's not related to qubits. So here's a look at what the data set looks like. There's actually 5,000 rows or so in this data set. There's 5 columns. The first column is the classification, whether it was negative or positive for being related to qubits. Second column is family ID, whether or not it's a member of the same patent family or not. The next line is the serial number. Then we've got the title of the patents. Then we got the publication dates. Just taking a look at the first few rows. The first few rows actually all belong to the same family, the first 10 or so rows. But if you look at the serial numbers, you can see they have different country codes at the beginning. So these are actually different patent applications that belong to the same patent family, but were filed in different countries. Now, in some cases, they filed multiple members of the family in the same country, like we can see 2 Canadian documents here and so on. But they're all members of the same family, so the titles are very similar. We can see that like 7 of these first 10 rows are all titled Detection of Electromagnetic Fields. But there's a couple that are called According to Signals of Electromagnetic Fields, there's one in another language, and so on. If we look down at the positive rows down here at the bottom between 3054 and 3061, all of those are actually U.S. patent documents. And they belong to several different families here. I think I got 3 different families. And you can kind of see, their titles and their publication dates as well. All right, so here's my project plan. I'm going to load the data, perform exploratory data analysis, do my data pre-processing and cleansing. I'll do my word embedding layer for tokenization of the patent title vocabulary. I'll create my models. And again, I'm comparing 3 different recurrent neural network models, LSTM, bidirectional LSTM, and a gated recurrent unit. Then I'll train the models, determine my validation accuracy for the models. And then I'll take the best performing model under validation accuracy and evaluate that model against the test data set. And then I'll have my analysis and conclusion. So here's a look at the exploratory data analysis. Upper left on the diagram is the distribution of the title length. X-axis is character count, y-axis is frequency. We can see we've covered most of the documents, probably like the 95th percentile, somewhere around 150 characters. But we can see the long tail goes out quite a bit, and we've got some titles that have over 300 characters. Same kind of thing for distribution of word count in the middle there. We've got about 20 words is probably the 95th percentile, but we got the long tail that goes out over 40 words for a title. And if we look down below those two diagrams, we then see it by non-qubit versus qubit related for character count and word count. We can see that the non-qubits patents tend to have the long tail has more characters and more words, whereas the qubit related tends towards shorter titles and word count and characters, which kind of makes sense. You know, some of our if we look back at my very brief description here, I have some titles like subflux quantum generator describing a hardware device. It's just 4 words. Whereas, you know, I have some titles like according to signals of electromagnetic fields, slightly longer title. But really, I mean, if we look at it anecdotally, you know, the words and characters looks pretty similar here. But again, we're dealing with a whole data set of 5,000 titles, not just the short 20 titles I popped up on that screen. On the right-hand side for target class distribution, we can see that there's slightly more non-qubit patents in this data set versus qubit related. There's over 2,500 non-qubit and slightly below 2,500 qubit related. And then I have a feature correlation metrics that also involves a heat map, and it's basically showing target versus title length versus word count. All right, so that gives you an idea of the correlation. All right, so here's my results once I created my models and ran them. So comparing the 3 models in this particular run, bidirectional LSTM came out best. And basically what these diagrams are showing, if we look at the diagram on the left, I've got LSTM training and validation in blue, with the solid line being training and the dashed line being validation. Bidirectional LSTM is green and GRU is red. So we can see that GRU is lagging behind LSTM, and LSTM is behind bidirectional LSTM, which is why bidirectional LSTM came out best. Similarly, we look over at the model loss comparison, we can see again GRU is kind of lagging behind LSTM, and then LSTM is kind of lagging behind bidirectional LSTM. Now, the other thing we notice when we look at this diagram is we rapidly got very high in accuracy within about 2 epochs. And we kind of, you know, by 4 epochs, we were pretty stable at where our accuracy was, very close to 1. If we look over our loss, again, by 2 epochs, we're really low on loss. And by 4, we're pretty stable on loss. And when I ran this learned algorithm against the final test set, I got a final test accuracy of 0.9765, which is very high, close to 1.0, rounding up to 97%. That's very high. So one of the questions I had was, why was I able to train it this well? Now, it could be, again, that if we looked at my data set, patent titles are created by patent attorneys through a very formal process. And so it could be this is a sort of problem that's very easy to learn for a machine learning application. Also, the patent title lengths, aren't that long. We saw some patent titles were like 4 words. Some of them were like 18 words, but most of them were less than 20 words, with some outliers going up to about 40 words. But we also had this patent family issue where, some patents are in a family of multiple patents, some patents are on their own. One question I had is, how much is patent families influencing my accuracy? So I decided to rerun this result, this time removing the additional patent family members. So there were 1429 unique patent family numbers in my data set. So I kept the first row from each patent family and removed all the subsequent rows. This time, my final test accuracy dropped down significantly down to 0.8287, 83% from 97%, a significant drop. Notice what happened on the epochs. If we look at model accuracy, last time I was pretty accurate by epoch 2. This time, no, we're still significantly learning after epoch 2. It's not till probably epoch 7 that we finally kind of are hitting a steady state. Similarly, if we look at model loss 7 and 8, if we look at model loss is improving all the way to, somewhere between 6 and 8, depending on the particular model we're looking on. And again, red, GRU was lagging in both cases, back to like Epoch 10 is when it caught up with the others. And in this particular case, LSTM actually did better than bidirectional LSTM. But in both cases, gated recurrent unit was way behind the other models. So why does the presence of additional patent family documents have such a big impact? Well, one possibility might be that our accuracy for second and subsequent members is 1.0. If that's the case, maybe we've got 0.82 accuracy on our very first entry for every patent family, and subsequent patent families, it's basically 1.0 accuracy. And so it sort of averages out around 0.96. 7 accuracy once we get to the combined data set. That's one possibility, but the math doesn't quite work out that way when I run if it's uniform distribution, which it's not. So it could be this is within the margin of error. Another alternative explanation is that the algorithm is also learning which vocabulary words are most important by analyzing different wording differences between the members of the same patent family. I.e., this is a big data answer, and more data leads to better results. So if we go back and look at our data set again, look at this very first patent family here. I've got detection of electromagnetic fields. That's a title for 7 of the entries in the patent. But also I have a couple entries where it's according to signals of electromagnetic fields. So the machine learning algorithm might learn that electromagnetic fields is the most important part of this title, and according to signals of or detection of doesn't matter as much. And therefore, the machine learning algorithm is actually learning from having these extra patent family members, even if it's learning where to put the weight on the words. And so that's one reason why having more patent family members in the data set can really help. So again, more investigation could be done to figure out exactly what was going on there. But, this has been an interesting experience. I learned quite a bit about how LSTM, bidirectional LSTM, and GRU process text information with regards to patent titles, and I was impressed with the accuracy rates for classifying patents based on title information. And this project really emphasized the value of fully understanding your data set and relationships within your data set. Thanks for watching.